Welcome to The Explainer. Today, we're taking an absolutely incredible anatomical road trip. We are going to trace the exact route of one of the most fascinating, literally vital structures in the entire human body, the seventh cranial nerve. So, buckle up, because we're following this superhighway from deep inside your brain all the way out to the tip of your nose and the very edge of your smile.
Seriously, think about it for a second. Have you ever wondered what actually lets you frown in deep concentration, cry at a sad movie, savor a hot slice of pizza, or instinctively jump at a loud noise? It's kind of wild, but how are these totally distinct everyday human experiences connected? Well, they actually all rely on the exact same biological pathway running right through your skull.
All right, let's dive right into this. We're talking about the facial nerve. It's the seventh cranial nerve, and while it's technically a mixed nerve, meaning it carries both motor and sensory signals, it is predominantly the master motor controller of your facial expression. Without it, your face would just be an unmoving mask. No expressions, no nothing.
So here is our roadmap for today. First, we'll pinpoint its start at the brainstem. Second, we'll track its journey through the skull. Third, we'll map out the 5 facial branches. And finally, we'll look at some clinical roadblocks.
Okay, pulling up to the starting line. Let's hit part 1, the seventh cranial nerve.
The journey starts deep down in the brainstem, specifically at a spot called the pontomedullary junction. Now, notice how the facial nerve doesn't just start as a single simple cord. It actually emerges as 2 distinct roots. You've got a large, thick motor root, which is the main facial nerve proper, and right next to it, a much smaller sensory root known as the nervus intermedius. Together, they leave the brainstem and head straight toward the tight, bony corridors of the skull.
And that brings us smoothly to part 2, journey through the skull. This is where the road gets incredibly complex.
This brilliantly illustrates our nerve's literal maze inside your head. Look at how it enters the internal acoustic medius right alongside the nerve responsible for your hearing. Once inside the petrous temporal bone, it travels through the facial canal in 3 distinct segments: the labyrinthine, the tympanic, and the mastoid segments. And right at the end of that labyrinthine segment, it makes a sharp, hairpin turn backwards. We call this the external genu, and it's exactly where the geniculate ganglion sits. It is a total anatomical maze in there.
But here's the thing. Our nerve isn't just a straight-through highway. It has exits. Before it even leaves the skull, it drops off 3 highly important passengers. First, the greater petrosal nerve branches off to control your lacrimal gland. Yep, this is the exit for tears. Next, it gives off a tiny nerve to the stapedius muscle in your ear, which actually dampens loud sounds, so the world isn't just unbearably noisy to you. And finally, the chorda tympani branches off to supply the taste buds on the front of your tongue and trigger your salivary glands. So tears, hearing protection, and taste all hop off the highway before we even reach the face.
Now, we are finally ready to leave the skull behind. Section 3, the 5 facial branches.
The main trunk of our nerve finally sees the light of day by squeezing out of the skull through a little hole called the Stylomastoid Foramen. From there, it curves forward, wraps right around the side of the styloid process, and buries itself straight into your parotid gland. That's the large salivary gland in your cheek. But wait, it doesn't actually innervate this gland. Instead, it just uses the parotid gland as a sort of staging ground to divide into 2 main trunks, which then fan out into its terminal branches.
Now, to remember exactly where these branches go, I want you to actually do this physical motion with me right now. Seriously, try it. Take your hand and place the heel of your palm right over your ear, over your auricle. Now, spread your 5 fingers out across your cheek and face. Congratulations, you just successfully mapped the exact distribution of the facial nerve.
Let's quickly look at those 5 fingers. Your thumb pointing up, that represents the temporal branch, which crosses your cheekbone so you can wrinkle your forehead. Your index finger is the zygomatic branch, heading to the eye to let you blink and squeeze your eyes shut. Your middle finger is the buccal branch, controlling your upper lip and cheek. Your ring finger is the marginal mandibular branch, running right along your jawline. And finally, your pinky pointing down is the cervical branch, diving down into the neck.
You know, anatomists centuries ago noticed this beautiful fanning pattern as the nerve exited the parotid gland, and they gave it a very fun, very descriptive nickname, pes onsurinus. That translates directly from Latin to the goose foot. And honestly, if you look at how those 5 branches radiate out, it really does look exactly like the webbed foot of a goose stamped right onto the side of your face. It's just nature's sense of humor at work.
Which brings us to our final stop, Section 4, clinical roadblocks and lesions.
So what actually happens when there's a crash, a compression, or an infection somewhere along this anatomical highway? Well, what's really interesting here is the distinct visual difference in paralysis patterns depending on exactly where a lesion occurs. We have upper motor neuron lesions, which happen high up in the brain, and lower motor neuron lesions, which happen down on the nerve itself. In an upper motor neuron lesion, like a stroke, only the lower quadrant of the face is paralyzed. But in a lower motor neuron lesion, the entire half of the face droops.
The absolutely crucial point here is understanding why the upper face is spared in those upper motor neuron lesions. It's because the muscles of your upper face, like your forehead, actually receive backup wiring from both sides of your brain. It's a built-in failsafe. So if one side of the brain has a stroke, the other hemisphere just steps in to keep your forehead moving. But if the facial nerve itself is cut or damaged further down the line, a lower motor neuron lesion, that backup is completely lost, and the entire half of the face goes totally slack.
The most common example of this is Bell's palsy. You can think of this as a major traffic jam right at the highway exit ramp. It's a lower motor neuron paralysis, usually caused by inflammation and compression of the facial nerve right as it tries to squeeze out of that tight stylomastoid foramen at the base of the skull.
Because the roadblock is right at the exit, all 5 of those goosefoot branches are shut down, resulting in some pretty immediate symptoms. The face is pulled asymmetrically over to the healthy side. The temporal branch fails, so there are no forehead wrinkles at all. The zygomatic branch fails, which means the person can't close their eye. And because the lower part of the eyelid sags, tears constantly overflow and just run right down the cheek.
Now, let's move backward along the nerve and see how this builds if we push that traffic jam deeper into the skull. If the lesion moves up above the chorda tympani off-ramp, you get Bell's palsy plus a loss of taste and saliva. Move it up past the chorda tympani onto the nerve to the stapedius, and you add hyperacusis, meaning everything sounds painfully, overwhelmingly loud. Move it all the way up to the geniculate ganglion, and you knock out the greater petrosal nerve too. That means you lose the ability to produce tears completely. It's a total cascading failure based entirely on the anatomy.
And sometimes, as the body frantically tries to repair the highway, it makes a wrong turn. This leads to a truly fascinating condition called crocodile tears syndrome. If the nerve is damaged high up, the fibers that are supposed to grow back down to your salivary glands get lost. They accidentally grow into the sheath of the nerve, leading to the tear glands instead. The bizarre result? Whenever the person eats and tries to salivate, they spontaneously start crying actual tears instead, literally getting their wires crossed.
Finally, we have Ramsay-Hunt syndrome. This is essentially a severe multi-car pileup on our neurological highway. It occurs when the herpes zoster virus, yep, the same virus that causes shingles, attacks the geniculate ganglion, right at that sharp bend inside the ear. Because it hits so high up the chain, it knocks out almost everything. You get complete facial palsy, loss of taste, loss of tears, and a super painful rash of vesicles on the outer ear itself.
And that, my friends, brings us to the end of our journey. From the brainstem, winding through the bony labyrinth of the skull, popping out into the parotid gland, and radiating all the way across your face. Next time you shed a tear at a movie, complain about a loud noise, or just flash a genuine happy smile, will you remember the incredibly complex, split-second road trip happening right inside your head? Your anatomy is an absolute marvel of engineering. Thank you so much for joining me on this explainer, and as always, keep exploring.